Hello everyone, welcome back to another minute concept, this time about Le Chatelier's principle. And this is the last video we'll have on most of the general chemistry to equilibrium topics. And this is actually one of the easier topics. So, how does the Chatelier's principle work? Le Chatelier, he's French. Basically, what he's trying to say is that equilibrium is like a seesaw, right? And when we have balanced stuff here, let's say that these two balls are the same, or rather than balls, let's make them blocks. So when these two blocks, think of this as the reactant side, and this is the product side. When they're equal and they're at equilibrium, the seesaw is balanced. Now, what happens if we add more on one side when they're already at equilibrium, right? So remember that equilibrium is a reversible reaction. So we'll just put that there. Let's say that we add more of the reactants. So we add this blue box, right? So naturally, the seesaw would shift this way, right? And it's gonna get heavier on that side now. How do we restore equilibrium? We restore equilibrium by adding another box on the product, right? Now, in actual equilibrium, what this looks like is the more reactants we add here, like this one, when we add a reactant, these reactants tend to form more product. This is the way. This is how it balances out the seesaw again. So the more reactant we put, the more it turns into a product in order to balance out the seesaw. Now, on the other hand, if we do it backwards, right? Let's say that we reverse this arrow and we decide to add more product. This side will get heavier first. We'd have more product that eventually turns into reactants so that we can balance out the equilibrium. Now, that's just off of concentration, right? This is the concentration factor. So similar to collision theory, we in collision theory we have the factors of concentration. We have concentration, we have heat, and we have concentration, heat, surface area, and catalysts, right? And catalysts, and we don't involve catalysts in equilibrium. Why? Because catalysts don't do anything to help you achieve equilibrium. It just makes the reactions faster. So catalysts are unapplicable here. Now, how about heat? All right. So how about heat? We're gonna shrink this just so that we can keep it here on the screen. For heat, it's different, right? So imagine a reaction given by A plus B turns into C, and the enthalpy is negative, right? Negative 100, let's say joules per mole. Now, this is an exothermic reaction. Exothermic. All right. Now, what does this mean? Okay, so when we have an exothermic reaction, basically what we're saying is this is also equal to the addition of heat. So we'll add a little plus sign here, plus heat, right? Now, if we elevate, let's say that we add heat to this system. Let's not use yellow because apparently my software can't recognize yellow that well. Let's say that we increase the temperature. That means we increase the heat, right? Now, if we increase the right side, then it has to shift to the left, right? The equilibrium has to shift to the left. So first thing we're gonna do is we're gonna change this symbol into like the reversible reaction there. So if we add more heat, the shift is going to be to the left because we need to balance them out. Now, how about if we decrease the heat? If we decrease the heat or decrease the temperature, we do the opposite. So we decrease the temperature, we decrease the heat, we subtract from this side, right? We're taking this away. So that means we need to shift the right side so that we can produce more heat. I hope that makes sense because basically what we're just describing here is the seesaw, and this time instead of it being in a pure drawing form, we actually can make it in terms of the enthalpy. we have our own little triangle over there. Oops. We have our own little triangle fulcrum there from enthalpy. And that's the general gist of how heat affects the equilibrium. Now, how about what if it's an endothermic reaction? So simply put, we're just gonna make this a plus sign, and we're gonna change this word to, hold on, I'm gonna change this word to endothermic. Right now, what is an endothermic reaction? When we say endothermic, we absorb heat, right? So we're gonna rewrite this. We're gonna absorb heat. So the heat is now on the left side. Plus heat is going to be reversible as it produces C. Right? Now, if we increase the heat, that means where will our shift go? We add to the left side, so the left side gets heavier. That means we need to make the right side heavier. So we add to the right side. It's a right-sided shift. It goes this way. Now, how about if we take away the heat? Let's say that we're going to decrease the heat. We're going to reduce from this side. So that means that the products have to go from right to left. It has to turn into a reactant. Now, really what we're doing here is just shifting the seesaw. We just want to make sure that it stays in the middle however way we can. If one side is too heavy, then we go to the other side, right? And that's pretty much how it works for heat. Now, how about another topic? Another topic that affects our equilibrium is, or not topic, rather concept, is pressure. Now, for pressure, we have to go back to the idea of collision theory. Now, when we say collision theory, we're basically describing how likely gas is going to, not gas, rather, how likely molecules are going to react with each other given the amount of collisions they have. Now, when it comes to pressure, the lower pressure we have, the more volume. So we need to determine that first. So pressure is inversely proportional to volume, right? Now, whenever we increase the volume, we reduce the pressure. Whenever we decrease the volume, we increase the pressure. So keep this in mind. Imagine if we have this jar filled with gaseous molecules. So what's a good example here? Let's say it's hydrogen gas. So it starts off as uniatomic hydrogen, and it's a reversible reaction between uniatomic hydrogen and diatomic hydrogen. Now, let's say that this is low pressure system, so we have like a bunch of the uniatomic hydrogen just flying around in there. So this is low pressure, high volume, right? Now, here, whenever, according to the Chatelier's principle, whenever we have low pressure, we favor the side with more moles of gas. So low pressure, shift to more moles of gas. Moles of gas. Now, what happens when we increase the pressure? Well, we can see that here. So let's say that I'll shrink this right there. Now it's a lot more cramped, right? And okay, don't mind the drawing, but basically now we're forcing them all to react with each other. And when we force them to react, what are they going to form? According to our reaction here, it says it's going to form diatomic hydrogen. So that means at higher pressure and lower volume, that means that we're going to have more of the product, or rather more of the side with less moles of gas. So higher pressure means shift to the to less moles of gas. Moles of gas. And that's it. So that's basically Le Chatelier's principle. And let's just recap a little bit. Le Chatelier's principle basically describes how equilibrium can shift based on stress applied, right? And when we talk about stress, it's basically just which side will have more of its constituents. So if we have more reactants on one side, then we need to shift to the product side. If we have more products, then we need to shift to the reactant side. Now that's based on concentration. How about when we talk about the Chatelier's principle in terms of heat? When we have endothermic reactions, when we increase the heat, that means that we need to shift it to the right because heat is part of the reactant side. You need heat to react. Now, when it's exothermic, it's the opposite. When you form the products, you produce heat. So if you increase the heat in an exothermic reaction or an exothermic system, we produce more reactants. Now, how about for pressure? Again, pressure is going to be one of the more straightforward ones. More pressure means more reaction, and you're compressing more. You're compressing the space, so you decrease the volume. So when you increase the pressure, you shift to the side with the lesser mole of gas. Now, when you decrease the pressure, you increase the volume. You make sure that the molecules have space to disassociate, they can separate from each other. So we have more moles of gas, and we can shift to more moles of gas whenever we have high volume and low pressure. So thank you everyone for watching. I hope you guys learned something from this video. The Chatelier's principle is really really simple to understand if you can spot how it works in real life application. And I suggest you guys take a look perhaps at concrete examples such as in the kitchen, because when you're in the kitchen, you do a lot of adjustments. If something's too salty, sometimes you might add a sweetener. If something's too sweet, you add something that will make it salty. That's an example of the Chatelier's principle. So that's it, and thank you everyone for watching. I hope you guys learned something, and that's going to be it for the Chatelier's principle. See you in the next video regarding acids and bases. Bye everyone.